So in this talk, I will discuss an information theoretic approach to distributed learning under communication constraints. And this is based on a few papers that were published in machine learning and information theory venues that were jointly co-authored with different subsets of these 5 people here. Leighton Barnes and Yanjun Han are both PhD students at Stanford. Berivan Işık is a soon-to-be PhD student at Stanford. She's currently an undergraduate at METU. Pritam Mukherjee is a postdoc at Stanford, and my colleague Saki Weissman. Okay, so let me start with just one slide of overview of machine learning to set the notation. So typically, we have a data set, right? So let's say n samples, and you can think of the xi's as labeled images, and we would like to learn a model for our data so that we can use it for things like prediction, predicting the labels of previously unseen images. And we do that by using what is called empirical risk minimization. You simply take a loss function, and then you find the model that minimizes the average of your loss function over your data set. And the loss function here, in this case, it captures the error you make in representing the ith sample if you choose your model to be equal to beta. And if you're training neural networks, then this beta would correspond to the coefficients of your neural network. And these days, neural networks have, the number of coefficients neural networks have are in the millions, right? So 10 million, there are even architectures with 100 million coefficients. So you can think of this beta as a very high dimensional, very long vector. And how do you do the minimization? Well, one of the simplest thing would be gradient descent. You simply compute the gradient of your loss function, and you move in the direction of the gradient. But even for large-scale machine learning problems, high-dimensional machine scaling problems, that turns out to be computationally too complex because if, let's say, you have 10 million coefficients, then so in order to compute the gradient, you would need to compute the gradient of your loss function with respect to each sample in your data set. And if you have 10 million coefficients, each of these gradient vectors will be of length 10 million. And now you have to compute it for every sample in your data set, which is also in the millions. Okay? So instead, what is done in practice is to use stochastic gradient descent, which simply means you take some random small subset of your data set and you compute the gradient with respect to that small subset, okay? And you can think of this G tilde T here as a stochastic or noisy estimate of this true gradient GT. Sorry. But even stochastic gradient descent can be too slow for when you're training large architectures over large data sets. And what people do sometimes or often is to try to speed up the computation by distributing it across many nodes. So imagine you take your data set, and let's say you split it over B nodes. Then you could do the following. Each node here can compute the gradient of the loss function with respect to only one sample in their local data set. They can communicate these gradient vectors to a central node, which can compute the average, and you get this stochastic gradient. But now, because you're doing big computations in parallel, you can potentially speed up the computation by a factor of B with this approach. But remember, each of these gradient vectors, right, if we have 10 million parameters, this is a real vector of length 10 million. So communicating these gradient vectors can require significant bandwidth, okay? And communication bandwidth can now become a significant bottleneck. So here is one experiment that was done by in the group of one of my colleagues at Stanford, where they do the following. They're training neural networks, and they are distributing the training over up to 64 nodes. And they observe that when these nodes are connected to each other with 1 gigabits per second Ethernet connections, then you get almost no speed up in training. But if you increase the network bandwidth to 10 gigabits per second, then you get a factor of 30 speed up. And the point of their paper is to say that if you don't communicate these gradient vectors as they are, but you do some compression, you can actually achieve that factor of 30 speed up on the slower network, okay? And I'll come back to this paper and distributed training of neural networks towards the end of my talk, hopefully if I have time. But now, since I'm talking to information theorists, I would like to kind of see if we can capture this problem, describe this problem by a simple mathematical model, and then do some theory around it, and then see if that theory can lead to any insights regarding the design of these systems, okay? So what is really the problem that we are trying to solve here? Well, we have data, right? And we are trying to learn a model for our data. If you take a statistical learning perspective, you would say we are trying to learn the distribution from which our data is coming from, or a suitable approximation for that distribution. Then maybe the question we would like to focus on is how do we learn distributions in a setting where our samples, our data set is distributed across many nodes, and nodes are limited in terms of how much they can communicate with each other. So kind of the simple mathematical model that I would like to propose is the following. So let's say we have n samples that are generated IID from an unknown distribution P, and these samples are distributed across different nodes. And these nodes are limited in terms of how much they can communicate with each other. And we are trying to obtain an estimate for this underlying unknown distribution P, okay? And when I say estimating the underlying distribution, I really have a few slightly different settings in mind. So maybe the underlying distribution is discrete. So in this case, I will assume that I know the alphabet. Let's say these are just integers from 1 to t. But I don't know the probabilities of these symbols, and this is what I'm trying to estimate. Or maybe my samples come from a continuous distribution. So this would be the so-called non-parametric setting, and I'm trying to estimate the density from which these samples are generated. Or maybe I have some side information, some information about the structure of this distribution so that I can parameterize it with a finite number of parameters. Let's say D parameters, and in general, I'm interested in settings where D can be very large because these modern machine learning settings are typically high dimensional, so the number of parameters I'm trying to estimate here, D, can be comparable to the number of samples I have. And in this last case, when my distribution is parameterized, the problem of obviously estimating the distribution reduces to estimating its parameters. And okay, maybe one kind of example for this last setting that you may want to keep in mind is the Gaussian setting. This is simply the setting where each of these samples come from a d-dimensional Gaussian distribution. They are IID, and you're trying to estimate the mean of that Gaussian distribution. This is called the Gaussian location model in the literature. And how do we model the communication constraint? You can model it in a number of different ways. So the simplest thing to say would be, let me assume that each sample here has to be mapped to a finite number of bits, let's say k bits, independently. So each node has to do the encoding independently of the other nodes. A slightly more flexible model would be what I'll call the sequential model. So this allows for a little bit of interaction between the nodes. So here I assume that nodes are ordered, and they transmit in a certain sequence, and transmissions are broadcasted so that each node can hear the previous transmissions, and its encoding of its sample to k bits can depend on what it hears from the previous nodes. And finally, you can also kind of think about a fully interactive communication model where nodes can interact with each other, freely interact with each other in order to communicate their samples, say through a publicly available blackboard. But still, we would want to constrain the number of bits. We would want to impose a communication constraint, and we will say the number of bits that are written on this blackboard by each node cannot be larger than k. And I call this blackboard model because this originates from this research line in communication complexity in theoretical computer science, and that's what usually they call it in that domain, okay? And there is a rigorous mathematical way of defining these protocols, but I won't go into details. The nature of our results is typically the following. We typically develop achievable schemes that either use independent encodings or sequential encodings. So they are simple in that sense. But when we prove their optimalities, we try to prove the optimality under this most general blackboard model. And this basically shows that even if even if the nodes were allowed to interact, you couldn't basically beat these simpler schemes. So this typically is the case in all our theorems. And at this point, we have, I think, a few results on a few slightly different settings: discrete distribution estimation, non-parametric estimation, parameter estimation, for which this Gaussian location model is one special case. And indeed, for this particular case, this Gaussian location model and its sparse version has been studied in the literature before us under communication constraints. And for the special case, our framework recovers the previous results in the literature. And we also close some logarithmic gaps between upper and lower bounds that were left open in the literature. We have results for logistic regression, some classification problems, and so on. I won't have the time to go to all this. So what I want to do is I'll just pick up one very specific problem. And this turns out to be the simplest one, discrete distribution estimation. And I would like to give you a flavor of just a flavor of the theorems we are able to prove. Okay? Okay, so we'll look at discrete distribution estimation. And let me kind of very precisely define the model I would like to focus on. So the model is the following. I have an unknown discrete distribution. And I know it lives on an alphabet of size d, but I don't know the distribution. I don't know these probabilities. And I have n nodes, each of which observes an independent, identically distributed sample from this underlying distribution. And then it has k bits. Each node has k bits to communicate its sample, which means that we need an encoding function at each node, which takes the sample and maps it to k bits. Okay? And this encoding function in general can also be randomized, and you can also allow for kind of shared randomness between the nodes. Okay, and then these nodes communicate these k-bit messages regarding their samples and to a central node, and the central node will need to output an estimate of the underlying distribution and will measure error with squared L2 distance. So if the true distribution, underlying distribution is p, and our estimator outputs p hat, then our error is the squared L2 distance between these two distributions. And note that the estimate will be random, right? Because it will depend on the samples we observe. So maybe in general, for a given estimator, we would like to look at its expected error. And this is its expected error when the true distribution turns out to be p. And I'll take a worst case approach. So I will say that if you give me an estimator, a strategy, I will look at its worst case performance over all possible distributions on an alphabet of size D. And our goal is to minimize, to jointly design these encoding functions at the relays and the estimator so that we minimize this worst case error. Okay? So this is my mathematical formulation of the problem. Okay. And so our goal is to characterize essentially this minimax error here. So to do that, let us first focus on the centralized case. Assume I gave you n samples that are generated IID from an unknown discrete distribution, and you want to estimate the distribution. What would you do? Well, the simplest thing you can do is just compute the empirical frequency of each symbol in your data set, and then output that as an estimate for its true probability, right? And this empirical frequency estimator, it's easy to do the computation, will achieve a minimax L2 risk, which would be like 1 over n, where n is the number of samples you have, okay? So now, what do you do in the distributed case? So what if now your samples are distributed and you only have k bits to communicate each sample? Well, the first thing to observe is that if k is larger than log t, then you are fine, right? Because your samples come from an alphabet of size d, and with log d bits, you can communicate the samples as they are, so you can achieve the centralized performance. But what if k is smaller than log t? In this case, you can consider this very simple strategy. Take your alphabet, which is of size d, and partition it into subsets, each of size 2 to the k. So the number of subsets you will have will be d divided by 2 to the k. Let's call that m, okay? So now I have m subsets and n nodes. I can assign each subset to n over m nodes, and each node will be responsible only for monitoring those 2 to the k symbols in its subset, meaning that are you sure? Okay, meaning the following. So they will look at their sample, and if it's one of the 2 to the k symbols they are responsible for, then they will signal that to the central node, and they can do that because they have k bits, and otherwise they will just ignore their sample, okay? And at the central node, you can use the same frequency, empirical frequency estimator, and if you think about this, you can convince yourself that what really happens here is that because each symbol gets monitored by n over m nodes, it's n over m, it's as if your sample size is now reduced to n over m, and therefore, this is the performance that you will achieve with the scheme. And even though this may seem wasteful, you can show a matching lower bound, at least matching in terms of the orders, and the constants are also pretty close. So this is optimal, okay? And what is this saying? This is saying that when k is small, so let's say k is equal to 1, our minimax L2 risk would be d over n. So this is a factor of d larger. There is a factor of d penalty with respect to the centralized case, but that penalty decreases exponentially with k, okay? Okay, so let me skip this. And what is really more interesting here is how you prove the lower bound, the impossibility results. And for this, we need to consider a basic problem, which I think is very natural. So let me just say what the problem is. So even though I talked about discrete distribution estimation as separate from parameter estimation, you can actually think of discrete distribution estimation as a parameter estimation problem, right? Because there are these d probabilities that you're trying to estimate. And what is the parameter estimation problem in statistics? Well, you have an underlying parameter theta. You observe a sample x, which comes from a distribution conditioned on, that depends on theta, and you are trying to estimate theta, let's say, by minimizing the mean squared error. And there is a classical result in estimation in statistics which says that your mean squared error, the mean squared error of any unbiased estimator is always lower bounded by the inverse of the Fisher information for that model. And Fisher information captures something about how informative your sample is regarding the underlying parameter. So what we need to do is to study a very natural variation of this problem, where now we don't have access to the sample as it is, but I only have an access to a k-bit quantization of the sample. The question is, how large can the Fisher information from a k-bit quantization of the sample be? How large can you make the Fisher information from a k-bit quantization of X? And we have a kind of a nice geometric framework which allows us to characterize this problem, and this basically allows to kind of prove those matching lower bounds in our results. So finally, I just want to say, basically, I started by talking about distributed training of neural networks, and then I talked about these more abstract problems, and I want to show you that you can actually relate these problems to the original distributed training problem. You can actually cast the gradient accumulation problem in distributed training as a parameter estimation problem. So you can think of the parameter that you are trying to estimate as the true gradient with respect to your objective function. And each node computes a stochastic gradient. So basically, you can think of it as a noisy observation of this parameter. And if you distribute your data set independently across these nodes, you can argue that these noisy gradient observations will be independent and identically distributed. They will be generated IID from the same distribution. And now you are communication limited in terms of communicating these noisy gradients. Let's say you have only k bits to communicate them. And at the central node, you're trying to construct a good estimate for the true gradient. Okay? The only thing I need to specify here is basically how I model the statistical relationship between these noisy gradients and the true gradient. Okay? And you can consider kind of different things here. So, I mean, this Gaussian location model has been studied in the literature. So you could say, what if I model the relationship between these noisy gradients and the true gradient as basically as if the noisy gradients are equal to the true gradient plus some Gaussian noise. Okay? So the noisy gradients correspond to the observation of the true gradient under independent Gaussian noise. So you could do that, but this turns out to be not a very good model for these gradient vectors. And you can see that in different ways. For example, if you look at the theory that you can do around this model, you will see that the final results will suggest that in order to achieve the centralized performance under this kind of a model, the number of bits you need should be linear in the dimension of these vectors. But what people have observed in practice is that you can actually maintain the baseline accuracy by significantly compressing these gradient vectors by using much fewer than d bits. And the key observation they seem to exploit in that is that these gradient vectors turn out to be sparse a lot of times. So if you do experiments, you will see that it's a 10 million vector, and many of the components, there are few components that have large magnitudes, and the rest will have magnitudes almost equal to 0. And what we essentially do here is to suggest a different statistical model. And for example, when we characterize the minimax risk for this model by using our theoretical machinery, you would conclude that the number of bits you need in this model to achieve the centralized performance would be of the order of S log d, where d is the ambient dimension, the length of these vectors, and S is the sparsity, which is defined in some soft sense. It's not exactly the number of non-zero components. And the more interesting thing is that if you take the theoretically optimal scheme here, and we tried it on a few real kind of data sets, we trained ResNet 18 on CIFAR 10 and CIFAR 100, we see that it can give you significant compression without losing, without sacrificing test accuracy. Actually, in a lot of cases, our test accuracy is better than baseline, where you communicate these vectors as they are, but our training accuracy is worse, meaning that the network generalizes better when you send these compressed gradients. And if you compare, for example, to this dip gradient compression paper, this was the paper I showed in the beginning of my talk, they achieve something like 99.9 compression ratio. There is a certain way you define it without losing any accuracy for your neural network, test accuracy. And we are able to improve roughly an order of magnitude over that without losing any test accuracy by using this kind of theoretically guided scheme. So this is all I would like to say. Thank you.